Suppose we play a game with a die where we roll and sum our rolls. We can stop at any time and take the sum as our score. But if we roll a face we have rolled before, then we lose everything. What strategy will maximize our expected score? And what is the optimal expected score? Note that we will only keep rolling if the expected sum of the roll exceeds our current sum. So let C be our current sum and S be the set of faces that we have rolled already. Then we can obtain the following inequality. Using the fact that the sum of our collection S is equal to our current sum, the inequality simplifies to the following. After our first roll, we only have one element in S, and C is less than or equal to 6. So C times S plus 1 is at most 12. Hence, we should roll again. After our second roll, we have two elements in S. Plugging in this number, C times 2 plus 1 is greater than 21. This means that C is greater than 7. Hence, we should stop if C is greater than 7 and roll again otherwise. After our third roll, we have three elements in S, and plugging in this number, we should stop if C is greater than 5.25. However, if we have made it to our third roll, then C must be at least 1 plus 2 plus 3, which is equal to 6. So, we should stop. As a result, our strategy is to roll twice. If the second roll is not the same as the first, and the sum is less than 7, we will roll again and stop. Otherwise, we will just stop right away. To find the expected score of our strategy, let us draw a tree diagram. For the first roll, we will have an expected score of 3.5. For the next roll, we will get 0 if we duplicate it with the last roll, and that comes with a probability of 1 in 6. Otherwise, we get an expected score of 7, and that comes with a probability of 5 out of 6. After the second roll, we will stop if our current sum is greater than 7. Otherwise, we will keep on rolling. For the stop case, we will assign an expected score of A with probability P. For the roll case, we will assign an expected score of B with probability Q. For the last roll, we may get 0 if our roll is duplicated with our previous two rolls, and that comes with a probability of 2 in 6. Otherwise, let us assign an expected score of C with probability 4 out of 6. To calculate A, B, P, and Q, we will reference the following table, which shows the count associated with different sums of two dice. This table excludes pairs like 1, 1, 2, 2, and so on, as we will get 0 if pairs occur. P is equal to the probability that our current sum is greater than 7. So we sum over all the possible cases and divide it by 36 minus 6 to get 12 out of 30. A is just the sum over all the possible cases weighted by the individual probabilities, so we get 55 over 6. Using the same method, we can get Q and B. After obtaining these values, we can update our tree diagram, and the only variable remaining is C. The following table shows all the possible current sums, and on the right, we have the expected value of the third row, assuming no duplications. Because if there are duplications, then we will lose our current score and get 0. Then, C is equal to the expected sum of our previous two rows plus the sum over all the possible expected value of the third row, weighted by their individual probabilities. Finally, we get C equal to 113 over 12. We have now completed our tree diagram. Therefore, our optimal expected score is 55 over 6 multiplied by 5 over 6 times 12 over 30, plus 113 over 12 multiplied by 5 over 6 times 18 over 30 times 4 over 6, which is equal to 223 over 36. Here is a follow-up question. Let us change the rules. Suppose we lose everything only if we roll the same face twice in a row. What strategy will maximize our expected score? Check out the answer below.